Well, relatively strong oxidizing agent. So when you go to the bar there, you can't order H2O2. You can order H2O. You don't want to change the composition. If you change the composition, you change the identity. Thus, you change the physical chemical property of the molecules that were present here. So pay attention when you're as a chemist there. You have to get into the habit of paying attention to these details. When you alter the composition there, you are changing the identity of the composition. So very important that you pay attention to the formula there. Now we have different types of formulas to represent different types of compounds there. One is what we call the empirical formula. Okay? The empirical formula basically gives you the simplest whole number ratio of what's involved in the molecule. Okay? And the other one is molecular formula. The molecular formula actually represents the actual molecule, the number of atoms of actual molecules involved in there. And the other one is what we call a structural formula. And when you have structural formula, you not only know how many each atoms are present, you also know how are they connected to one another. Okay? So these are three different types of formulas. Okay? And empirical formula, and again, by definition, we need to know how to define empirical formula. Empirical formula gives you the relative number of atoms of each element in the compound in the smallest whole number ratio. So the empirical formula for water would be H2O, 2 to 1 simplest whole number ratio. You can't get simpler than that. The empirical formula for H2O2 would be one-to-one ratio. 2 to 2 ratio, you can simplify that to 1-to-1 ratio. Okay, so you can see sometimes a compound, the molecular formula is, well, this is also what we call the molecular formula. The molecular formula is the represent the simplest whole number ratio, then that's your empirical formula as well. But sometimes the molecular formula is not representing, does not represent the simplest whole number ratio, then you end up with different representation. So empirical formula again gives you the simplest whole number ratio. The molecular formula gives you the actual number of atoms of each element in a molecule. The actual number of atoms in a molecule of hydrogen peroxide, H2O2, is that for every molecule of hydrogen peroxide, you got 2 hydrogen atoms, you got 2 oxygen atoms in there. Okay, so that's the difference between the molecular formula and the empirical formula. Okay, so for different types of compounds there, organic compounds for that matter especially, we can have butane, carbon 4, hydrogen 8. Now, the greatest common factor is 4, so the simplest whole number ratio in empirical formula would be carbon 1, hydrogen 2, CH2 would be the empirical formula. This, however, would be the molecular formula. Okay, boron hydride, B2H6. Okay, the simplest formula would be BH3, but the molecular formula would be B2H6. So you can see, and carbon tetrachloride, for that matter, the simplest whole number ratio is 1 to 4. So the molecular formula and empirical formula are the same. So this is something that you need to pay attention to. Molecular formula and empirical formula, sometimes they are the same, sometimes they're different, and depending on the molecule itself. Okay, so in terms of the structural formula, it also indicates how the atoms are connected to one another. In hydrogen peroxide, for example, H2O2, this is how the atoms connected to one another. That's the only way many of the atoms are connected to one another. That's hydrogen to oxygen, oxygen to oxygen, oxygen to hydrogen. No other way connecting these atoms together. You may ask why? Well, it has something to do with the number of electrons each atom has. And hydrogen can only take 2 electrons when they combine with other atoms there. So you cannot put hydrogen in the middle of 2 other atoms there. In that case, you're forcing hydrogen to take 4 electrons. Hydrogen say, I don't have enough room to do that. I can only accommodate 2 electrons there. So hydrogen is always going to be on the end, either on the left hand or the right hand, it doesn't matter. And hydrogen has to be what we call a terminal atom in any molecule. You can't put hydrogen in between 2 atoms there, because in that case, this little dash actually represents a pair of electrons. And you are forcing hydrogen to take 4 electrons there. if you put hydrogen in here, and will be another atom connected to it, another atom connected to it, then hydrogen will have to take in 4 electrons there. Hydrogen don't have enough room to do that. We will get into the details about the molecular structure. We'll get into the details about the covalent bound molecules in chapter 8, chapter 9, or the later this semester. Okay, so 3 different types of formula, and the empirical formula, the molecular formula, and structural formula. Structural formula is especially important if you're going to be taking organic chemistry. When you take organic chemistry, you know organic compounds, they have, if you just use the molecular formula to represent compound, many compounds, they can have the same molecular formula, but different structural formula. We use the term isomer to differentiate them. So compounds with the same molecular formula but different structure are isomers of one another. Now, most of the time, isomers will have completely different physical chemical properties. So when you study organic chemistry, and you have to pay attention to how they, not only how many atoms are in each molecule, you also have to pay attention to how the atoms are connected to one another. Okay, so for now, in Chem 101, we introduce these different types of chemical formulas to represent the different things there. So you need to know their definition. You need to know what's the difference among those different types of formulas there. And also, chemists are just like little kids. They always play with their Lego pieces there. So sometimes we use what we call a molecular model to represent molecules there. And by convention, hydrogen is represented by a white ball, a little ball with a white color. Carbon is black. Nitrogen is blue. Nitrogen, well, that's a lighter blue there. Oxygen, normally we use a red color. You get fluorine, phosphorus, sulfur, and chlorine, so on and so forth. So you play with the model there, and with a little stick connecting 2 balls together, and you end up with different models. So this is what we call a ball and stick molecular model. And it's especially important in organic chemistry because it gives you a very visual look on how atoms are connected to one another, and how atoms are directly connected to one another gives you a lot of the information regarding the property of the chemical, the physical and chemical property of the chemical itself. So another representation of the molecule, we need to know their structure, so we can use a ball and stick model to represent a molecule there. Okay. How do we name? Well, when we first introduced matter, we say, well, there's different classification there. Under the big group of matter, we have pure substance, mixture, and pure substance, we have element and compound, and so on. So how do we classify compounds there? For pure substance, we have elements. Elements could be atom, or could be molecule. Okay, and that's pure substance there. And then we have compounds there. In the compounds there, we have molecules, and we have molecular compounds, we have ionic compounds there. So those are the different types of categories of pure substance. Yeah. Now remember, we do have ionic compound there, and that represents the formula. The formula represents the simplest whole number ratio. Now you do not use the term molecule to describe ionic compound. Okay, molecule is reserved for molecular compounds, or covalent molecules there. Okay. Now how do we name these different types of elements and compounds here? Well, some of the atomic elements there, well, they exist in nature in singular form.